this lecture, we're going to be explaining water in the soil and the importance behind this. The learning objectives here are what forces act on water in the soil, what types of water are in the soil, and how does water move in the soil? How do plants get the water out of the soil, and how much water is in the soil? So now we ask ourselves, what are the forces acting on water in the soil? And these forces are adhesion, cohesion, capillary, soil moisture tension, soil water potential, gravitational potential, and osmotic potential. So you guys know what gravity is, right? So gravity pulls water down through the soil. But what happens after this? Well, we have adhesion. And adhesion is the pull of soil particles. This gravitational force pulls water downward, where adhesion force pulls the water side to side, but it may also pull it downwards as well. But it's pulling the water particle to soil particles. That's where that adhesion force comes from. Gravitational force is just going straight down. Adhesion force, you need that water particle, needs that soil particle to adhere to, okay? Now with cohesion, it is similar to adhesion, but with adhesion, the water particle is going towards the soil particle. Here, the water particle is going to another water particle. Now, let's just discuss some basic chemistry involved here. So we have hydrogen, and hydrogen has one proton, and that's a positive charge, and then one electron, which is a negative charge. So we have one positive, one negative. Oxygen has 8 protons, so that's 8 positive charges, 8 neutrons, which is 8 neutral charges, and 8 electrons, which is 8 negative charges. So we combine those and we get water, and we have a polar molecule. And what is a polar molecule? It has partial positive and partial negative charge from polar bonds. So here you can see where we have the negative charges and we have the positive charges, but they're even. Now we have hydrogen bonding, and hydrogen bonding occurs through adhesion. And this adhesion force is the force that is responsible for the attraction between water and solid surfaces. Now we have silicone, which has 14 protons, 14 neutrons, and 15 electrons, and has most of the common elements in soil particles, as you see now. And now with that combination of the silica and water, that's where that hydrogen bonding occurs. And that occurs through adhesion force. Because we have the silica from the soil particles, and then we have the water as well. And those are adhesing together. Now we have capillary action, and this is also referred to as capillary motion. And this is a combination of cohesion and adhesion and surface tension forces as well. So capillary action is demonstrated by the upward movement of water through a narrow tube against the force of gravity. This capillary action occurs when the adhesive forces between a liquid, such as water, and the solid surface, which would be the soil particles, of the tube are stronger than the cohesive forces between the water molecules. Now we can see in this photo that water in the soil is held in, you can think of it as almost like a film. So the first film is tightly held by adhesive water, and the second film is loosely held by cohesive water. And the adhesive water is held so tight it cannot be removed whatsoever, compared to the cohesive water that's not held so tight, so it's probably more prone to be removed. Now, soil water potential is the ability for water to move or do work. This is when it moves from high potential to low potential. Or you can think of wetter to drier, right? We have the high potential and then the low potential. And with higher potential, water potential, it is easier for the water to move in the soil compared to having low water potential. The water potential is going to have a weaker adhesion farther away, which has a weaker adhesion, higher potential, and easier to pull away, compared to particles closer, which has a stronger adhesion, lower potential, and it is harder to pull away. Now we have three types of water potential that includes matrix, gravitational, and osmotic. Now with the matrix potential, it has an attraction of soil particles. So this depends on how close the water droplets are to the soil particle and how attracted the particles are to each other. So here we have a water particle that is closer to the soil particle compared to a water particle that is further away. So which one is going to have more matrix potential? And the one closer is going to be strongly attached to that soil particle. Now, the gravitational potential is how much water above the water table seeks to be at the water table. And the osmotic potential is when the water particles are being pulled through soil by charged ions of salt. And these three are very important terms to learn. We have wilting point, which is the permanent wilting point. So we can have permanent wilting point at P, WP, or wilting point at WP. And this is defined as the minimal point of soil moisture the plant requires not to wilt. So how dry can the soil be to the point where the plant is not going to wilt? And now we have field capacity. And field capacity is the amount of soil moisture or water content held in the soil after excess water has drained away through that gravitational force. And the rate of the downward movement has decreased. So the field capacity usually takes about 2 to 3 days after rain or irrigation to really get the field capacity. So this is to the point where all of the water drains through and saturates the soil to the point where it has just enough soil moisture that it is content, and to the point where it doesn't need any more soil moisture at this time. And now we have saturation. Soil saturation is the condition where all of the drained water is already drained through the soil particles, and they are permanently filled with water. So these pores are permanently filled with water. And it's to the point where it's completely filled with water, it cannot hold on to any water anymore, and it starts dripping through. Okay, so here we have adhesion, which adhesion water is located first right by the soil particle. And with this, the wilting point follows it, or with the wilting point following with the pore space filled with water at 25%. And then we have field capacity, which is 25%. And then following that, we have the saturation point, which is 100% with the pore space filled with water. Here's a graph showing the inches of water per foot of soil depending upon soil texture. The water is not available for the first couple inches due to the soil needing X amount of water. The available water is in the middle where the soil can use the water, and gravitational water will not be used by the soil and will automatically drain through the soil since the soil particles are already saturated. And then we also look at wetting fronts, and the wetting front for clay soils are more towards the top of the soil and are larger in width due to the micropores and the high water holding capacity compared to sandy soils where there are an abundance of macropores and drains quicker. So the wetting front will be more vertical than horizontal.